Hello everyone. In this video, we will see how to remove information from inside a neural network model. We will present Irene, a method to achieve information removal at the bottleneck of deep neural networks, which explicitly minimizes the estimated mutual information between the features to be kept private and the target. A lot of interest around the biasing is indeed devoted because it would be irresponsible and unethical to promote algorithms that could possibly create damages or lead towards discrimination of people whose data are used by the artificial intelligence. For example, the European Union has already obtained the role of legal influencer as far as the discipline of data protection is concerned about drafting the General Data Protection Regulation. Since 2018, it has been working in trying to create the conditions to regulate artificial intelligence. Unfortunately, when we train deep neural networks, it's not that easy to discriminate between what is the information we desire these models to learn and what is the information being actually learned. For instance, for the simple case in which we decide to classify people having blonde hair and people not having so, we know what is the information being propagated, but we're not sure what is some extra side information being propagated as well from the model. And we don't even know whether that information is actually used by the model itself. So in this work, we try to stop the propagation of extra unwanted information inside the deep neural network model at some bottleneck layer. Well, what is then the literature we should compare to? Intuitively, we should work within the privacy preservation domain, where approaches like differential privacy are state of the art, or where, for example, federated learning approaches are being very used, for example, in sealed data pools for hospital and for treating medical data, for example, and where cryptography is also very well used in order to protect data. But actually, we are closer as an approach to all the set of approaches working on the biasing domain for deep neural networks, where, for example, there are works that remove the bias at the dataset level, like with balancing, cleaning, generating new samples, and so on. They can work even at an ensemble level. For example, they can train a committee of experts. Each of them can have a different bias, and then they can use them in order to average out the bias itself. So that's another approach. And there are even works which try to work or to remove the bias from inside the model itself. They constrain the learning process of the neural network model itself in order to discourage the learning of such biased information. So theoretically, we should be among privacy preservation models. However, we operate inside deep learning models themselves. Hence, we will mainly compare with the biasing approaches, which claim to remove the biased information. However, as a disclaimer, our goal is different from the biasing approaches. While those approaches do not target explicitly information removal, but they want to maximize the performance on unbiased data sets using biased data, our goal is to really remove the information from the neural network. We have no expectation with respect to improvement of performance on the model itself. So here comes the question: how do we remove information at the bottleneck in deep neural networks? Well, we have our input X and we forward propagate it through the model. We split the model into parts. We said that we have a feature extractor F and the task related head G. In the end, in order to train F and G, we need a loss to learn the target task. And so we have a task-related loss, L, which is going to be minimized. The joint between F and G, we name information bottleneck. And at such bottleneck, we attach a second head. We call it information removal head. The purpose of H, in this case, is to learn how much private information is possible to extract from Z. So we need as well to train this H term in order to learn the private information which arrives at Z. At this point, we need the real strategy. So how can we practically remove this information? And towards this end, we need a third term, which is I, a mutual information between the information being extracted by H and the ground truth information, which is associated to the current example being propagated. Namely, we know how much the information removal head is being wrong with respect to the extraction of the private information. And of course, we use the mutual information formula, which is quite standard. We use a smoothened version of it, in which we, as extracted information, we use a softmax from H. And as ground truth, we simply use a frequency-based estimation. But at this point, here comes a question. Why can't we use a simple gradient inversion approach? Namely, why instead of having all of this complicated plant, we can simply take the loss for the information removal head, and instead of minimizing it from H, we maximize it through the whole neural network, as being done in other scenarios. Well, the problem is that in this specific case, maximizing the loss does not remove the information. Let's say, for example, that the private information here is related to the class number 2, and we maximize the loss. What we obtain is the graph here on the right. But can we see really that the information is removed? In this case, the information is still there, because for instance, instead of taking the maximum of the probabilities, we take the minimum. So the information is actually still there. What happens when we have, on the contrary, mutual information minimization? Well, we have a uniform distribution for the probabilities. So we cannot really extract any sort of information, and we accomplish to our goal. And here comes the fun part, how to backpropagate the signals. Well, for the task-related loss, we backpropagate it through G and F with no problem, in a vanilla way. For what it concerns the loss for the information removal head, we simply backpropagate it through H, and we stop. We want just to train H to extract the information from Z. We do not want to encourage also F to extract that information from X. For what it concerns the mutual information term, we need to be very careful, because we need to backpropagate it through F, because we want to minimize this mutual information. But we do not want to perturbate the extraction of the information from the information removal head. So we have to backpropagate it through H, but for H, we have no gradient contribution for the parameters. Namely, we have to backpropagate it through H, but the parameters are not updated in order to minimize I as well. We need to be careful about this step. And so, just to summarize, the task-related head receives just contribution from the loss related to the task. The head related to the information removal H receives the contribution just from the loss, which helps to extract the information from the bottleneck, the private information from the bottleneck. And the backbone F receives contribution from both the task loss and the mutual information. And this is regulated through two hyperparameters: alpha, which weights the loss related to the task, and gamma, which balances the loss and regulates the contribution of the mutual information. We have performed experiments on two datasets. The first one is biased MNIST, which is essentially the MNIST dataset with colored background. And the task here is, of course, to simply classify digits. In this case, the background is the information we decide to keep private, and this dataset allows us to regulate an hyperparameter rho, which indicates how much a given class is aligned to some specific background color. In this case, in order to evaluate also the effectiveness of other concurrent techniques for the biasing, and actually to see how much information are they really removing from the feature extraction part, we train also in those cases head H, but of course it is not going to be used in an IRENE-like setup, except for IRENE technique itself, of course. And we see that across many different values for rho, IRENE, of course, remains to around 10% of color prediction accuracy for H, which is a random guess, while all the other approaches have consistently higher prediction accuracies, in which none of them actually really approaches 100%, except for learn mixin in very low rho setups. And if we want to look at the digit prediction accuracy versus color prediction accuracy, which we want to maximize the digit prediction accuracy, so being in the rightest part, and we want to minimize the color prediction accuracy, so we want to be in the lowest part, so we want to be in the bottom right corner, we see that IRENE places nicely exactly there. even when compared with the biasing approaches. This gives us hopes in using Irene also for the biasing, potentially. We also wanted to perform experiments on another datasets, namely CELEB, in which the training set here is balanced with respect to information to protect. In our case, it's the gender. And the task here is to learn one attribute among having blonde hairs, wearing heavy makeup, and wearing eyeglasses. Here, we are going to present just one of the three target attributes, and the other two are presented in the paper. And we see, for instance, that all the approaches, including the baseline, have very high prediction for gender, but with Irene, we see that the performance is minimally impacted, and we can really practically remove information related to the gender, approaching 50% of classification, which is essentially random guess. To conclude, what we see is that actually the biasing approaches, despite maximizing the performance, are not really removing the biased information. They're simply reweighting it. And of course, this can produce some result which is unbiased for the tested task, but this doesn't mean that they remove the information or that they do not use the biased information. They are, in synthesis. Irene, what it does is that, on the contrary, removes the information we wish to keep private at the bottleneck. And it could improve the performance, but we have a main drawback in using Irene, which is that we require the labels for the information we want to keep private. So Irene can be very effective in order to remove information, but it cannot yet be used for the biasing approaches. We are working currently on the development of a version built on top of Irene, which works for the biasing in an unsupervised setup. Namely, we do not know what the bias is in the dataset, and we want to remove such an information in order to maximize performance on the task. Thank you so much for the attention, and I hope to see you at the BMBC.